Another extremely common use for all this uncertainty calculation is testing hypotheses. Now, if you're a scientist, you're often going to come up with a hypothesis, an idea, and you want to test if it's true. Same applies often for research engineers. So let's say, for example, you hypothesize that eating chocolate makes students do better in physics exams. Seems like a reasonable hypothesis to me. If that was the case, well, how would you test it? Well, you might take your class, divide it in half, and in random, and give half of them chocolate before the exam and half not, and then see how they did. The trouble is there's going to be an uncertainty, because not all students do equally well in physics exams, and it could just be that randomly the half that you chose one way has a different ability at physics than the other half, say. So there's going to be an uncertainty. Or let's say you're an engineer and you work for a tyre manufacturing company, and you've got some new type of tyre that you think is going to reduce road noise. So you might test it, you might put your new tyres on a bunch of different cars and drive them on different roads in different conditions, measure the noise at a certain distance, then do the same with the old tyres and compare the two. Once again, there's going to be uncertainty because the conditions are never quite exactly the same, the cars are driven differently, the roads are different, the weather conditions are different. So if you see a difference, for example, let's say you discover that the new tyres, the noise goes down by, say, 4 decibels, but there's an uncertainty of 2 decibels in your number, can you actually say with confidence that your tyres really work? Likewise for the chocolate. Let's imagine that the class that ate chocolate scored 5% higher, but there's an uncertainty of 3%. Is that actually conclusive proof that chocolate is good, or could it just be a random fluke? Now, the crucial idea for how we test this is what's called the null hypothesis. You can never actually prove that your theory is correct. No matter how much data you have for a wonderful seeming theory, there could always be some new data that comes along tomorrow and proves it wrong. What you can do is prove the opposite wrong. And that's what the null hypothesis is all about. So, for example, let's say we've got our chocolate theory. Eating chocolate makes you do better. We can't prove that true, but we can come up with a null hypothesis, which is that chocolate makes no difference. Usually the null hypothesis is the boring thing, the inconclusive thing, and you're trying to prove that wrong. So chocolate makes no difference would be the boring, inconclusive answer, and we're trying to prove that wrong. For the road tyres that reduce the noise, the null hypothesis will be there's no difference between the noise with the new tyres and the old tyres. And again, we're trying to prove that wrong. So here's how you do it. What you do is you say, let's assume the null hypothesis was true. The chocolate makes no difference, that the new tyres make no difference, whatever it might be. What are the odds that we get a result as big as we see just by chance if the null hypothesis was true? And that's the one-tailed distribution that we've just been talking about, one-tailed probability. So, for example, chocolate, we've said that the people who ate chocolate scored 5% higher, but there's a 3% uncertainty. So if the null hypothesis was true, there should be a difference of 0, a mean of 0 and a standard deviation of 3. So what are the odds if you had a mean of 0 and a standard deviation of 3 that you get a result as big as 5? So we've got to do the one-tail distribution for n equals 5 over 3. Similarly, if you, for the road tyres, we've assumed that the uncertainty is 2 and we found a value of 4 decibel reduction. So the null hypothesis would be there's no difference between the two. So you expect it to mean of 0, standard deviation of 2. So what are the odds if you had mean of 0, standard deviation of 2, that you'd actually get a difference as big as 4? So that's n equals 2, which is for a one-tailed distribution, is a 2.5% probability. Now the probability is a probability that you would get this big or bigger a difference just from randomness. And you want that probability to be, it's called the p-value, to be as small as possible. If that value is very small, you can say it's extremely unlikely that we'd get this result just by chance, so there probably is something interesting going on here. How small does a p-value have to be? Well, in the social sciences, economics and so on, typically a p-value of less than 5% is acceptable. So if p is less than 5%, which normally corresponds to being about 2 standard uncertainties away, then you'll probably say, yes, this is significant, and we can publish a paper. On the other hand, in the physics and astronomy, we're a bit more rigorous about these things, and we generally prefer p-value of 1% or less, or even 0.1%, which corresponds to 3 or 4 or even 5 standard uncertainties away. Now, what I've just told you is the standard approach. It's very, very widely used, but I should warn you, this is actually extremely dangerous, and a lot of people abuse it. One of the most common ways to abuse it is what's called p-hacking. Take our chocolate example. We're trying to prove that chocolate makes students do better. But let's say you're a young researcher. You really need to publish papers to make your career. Unless you publish a large number of papers, you won't get grants, you won't get permanent jobs. So there's enormous pressure on you to get results. And you can't publish unless you get a p-value that's smaller, for the social sciences, less than 5%. So let's say you did the survey and the p-value came out as 10%. You can say, well, people who make chocolate did do better, but there's a 10% chance it's a random fluke, so it's not really enough to say anything very much. But what might happen at this point is you think, well, maybe chocolate doesn't help physics students, but maybe it helps art students. So you test some art students. That didn't come out at 5% either. Maybe it works for high school students, but not university students. We'll try that. That didn't come out. Maybe coffee rather than chocolate works. And you keep on trying more and more things until you eventually find something that is significant at the 5% level. So the p-value is less than 5%. If your p-value is small, we call it statistically significant. It doesn't mean it's actually important, but it just means it's a reasonably small chance that it was due to randomness, so you can publish it. But let's say you've tried 20 different approaches until eventually you found one that had this p-value less than 5% that was statistically significant. So you publish a paper and it looks really good. We found that coffee, when applied to high school students, made their English scores go down, or whatever it might be. What you hadn't mentioned is that you actually did another 20 experiments before you found the one that's statistically significant. And therein lies the problem. If you do 20 experiments, you'd expect one of them to show up at the p-value of 5% just by chance. So in fact, this is complete crap. It doesn't tell you anything. So be careful. This is the commonly used technique for testing hypotheses, but it is very dangerous and very open to abuse.